Just use my. That is okay. Press. It's off. Good afternoon, everyone, and a very warm welcome to all of you. We are today deeply honored because we are holding this talk in the auditorium for which the inspiration came from Professor S.V. Rangaswamy and Professor S.V. Rangaswamy's family. I think the first thing that we should do is to give a wide applause to Professor S.V.'s family who are here. Srimati Nirmala Rangaswamy is here, Amod is here, and we have a very special guest today, Dr. Vidya, who happens to be Professor S.V.'s daughter-in-law. So you can see so many things have combined today. I fondly remember Professor S.V.R. Way back in 1982, when most of you here were not born. He taught me data structures and algorithms course in the CSA department. And it was a lovely course. And then beyond the course, he also taught me how to speak and write English, because those days my English was very poor. So if I'm able to speak a bit in English these days and also write reasonably well, I think the credit must go to Professor SVR, who was actually, he had an obsession for, high quality English. And he actually used to teach all of us, all the students, a bit of English in every class. And that's how we remember him very, very fondly. And he was one professor who also used to like me very much. And he was loved by all the students. And, when Professor SVR, unfortunately, we lost him a few years back. And then the family came up with a wonderful gesture. They said, we would like to give back to the Department of CSA. And when the chair Professor Vinod Ganapati, mentioned to them that we are trying to build a new auditorium in the Department of CSA, immediately they donated an endowment, which was, responsible for, creating this wonderful facility that we have. So in some sense, this is a lovely context for this talk. We should welcome Dr. Vidya, daughter-in-law of Professor SVR, to be giving a talk in the auditorium for which Professor SVR was responsible. So, madam, welcome to you again, and welcome to all of you again. I will now, request Professor Vijay to introduce the speaker today.
Thank you very much. Good afternoon, everyone. It's a pleasure to have Vidya here. So Vidya is the Senior Director at Tableau Research, I think for many years now. So at Tableau Research, she is leading a team at what Tableau does really well, which is bringing together kind of the state-of-the-art in visualization, applied ML, databases, historically speaking, as well, and more recently NLP, to build kind of software that is really useful for the industry, and it's become kind of the de facto standard for visualization software out there. She did her PhD from Northwestern. This was in graphics. But I think she jumped into visualization, which is good for the community. She is a leader in the community at Infoviz. And more recently, I think it's been, 3 years now? I think she's also written a book on functional aesthetics for data visualization. Do check it out. But today she's going to talk to us about kind of how to bridge the gap between kind of human sense making and kind of the automated tools that we have, which I think comes in the word semantics here. That's my understanding of it. So over to you, Vidya. I'm looking forward to your talk.
Thank you so much for the kind introduction, Professor Narahari and Professor Vijay, and thank you all for attending, both in person and online. Really delighted to be here. So as Vijay indicated, this talk is kind of a premise of a collection of research that myself and the group has done. Oh, thank you. Thank you. And so it comes in three parts. If you have any pressing questions during the presentation, please raise your hand. But if you have any questions that require more longer term discussion, just feel free to hold it towards the end of the talk. Okay, so let's set the stage here. Humans are inherently driven to make sense of the world around them, whether it's having a fun dinner with your friends or having a meeting at work or simply just observing nature. And meaning is a rather abstract concept, and semantics is a concrete way of expressing that meaning in information. So this constant search for meaning is at the core of how we interpret information, from decisions to communicating insights. And in the context of data, statistical graphics like this brain to body mass plot that you see here by Carl Sagan is rather abstract, because in order to make sense of the relationships, your eyes need to follow the labels, the dots, and the arrows that match the labels to the dots. And it's really hard to glean key insights from that. So our goal in the field of data visualization is to really design representations that align with how people naturally interpret data. So here is the variant of that same chart. And this is by Edward Tufte, where the icons are semantically appropriate and align with the data set to reinforce the meaning. So you can see this hummingbird at the bottom with the various animals and how they stack up. Let me just try to close that so that it doesn't occlude the. Okay, is that better? Yeah. So this basic premise of adding meaning to charts motivated some of the early work that I did with Jock McKinley back in Tableau to come up with algorithms to automate semantic icon encodings for visualizations. So by embedding semantics into visual representation through meaningful icons, contextual defaults, and real-world associations, we can arguably make data more intuitive and interpretable. But beyond these individual design choices, a larger question emerges. How can we systematically integrate meaning into data interactions to enhance human understanding? So this brings us to the core research question that drives a lot of my work. How can we leverage semantics, language, and visual representation to create these intuitive and intelligent data interaction systems? So in this talk, I will discuss three main research directions that shape my work. The first one is employing semantics for meaningful data representation. The second piece is conversational interfaces. The third aspect is how we can effectively integrate visual and textual narratives to create more expressive and insightful data stories. And finally, I'll talk about some future research ideas in this space. So let's explore each of these topics in more detail. So the first problem is designing visualizations that inherently convey meaning using both perceptual and linguistic cues to enhance interpretability. So let's start with an example. We found that many visualization tools, including Tableau, are optimized for perceptual legibility, and they often fail to reflect the natural associations between data categories and colors. For instance, in this bar chart illustrating vegetable prices, Tableau's default palette might assign blue to tomatoes, pink to corn, and so forth. Unless you're using genetically modified, vegetables, this is really, not the case. So we find that users painstakingly associate custom colors with their categorical values in their data, like this example from Tableau Public. where Tableau Public is a free online platform that allows users to create, share, and explore interactive visualizations. And this process gets even more tedious and tricky as the data increases. So the problem motivated the need for us at Tableau to develop an algorithm that could automatically associate or assign semantically meaningful colors in visualizations. Here are two examples to show how a human manually colored this data, along with the version generated by our algorithm below. So what were the design choices that influenced how we approach this problem? First of all, colors should be perceptually distinguishable to avoid confusion and work for different mark sizes and backgrounds. So it's important to use semantic associations where possible, like blue for water, green for nature, and so on. Also, color and language are deeply intertwined, influencing how users interpret and recall color assignments and visualizations. A lot of the foundational work by Berlin and Kay, along with follow-up research, established that cultures develop color terms in a universal sequence, reinforcing that certain colors are cognitively more salient. So one approach is to leverage large text corpora to understand how colors are commonly described in relation to objects. N-grams analysis allows us to identify frequently co-occurring color object pairs in natural language. Google Ngrams is a publicly available corpus of large volumes of digitized books and documents. So using this corpus, one can obtain various types of co-occurrence statistics containing phrases of N terms called Ngrams. So here's a screenshot of that interface. And as you can see here, banana and yellow are co-occurring much more than, say, banana brown or banana black. So this indicates that banana is strongly associated with yellow. And here are some sample books and documents on Google Ngrams. The text snippets here show the co-occurrence of the term banana with one or more of the basic colors. And as you can see, banana and yellow occur together frequently. This table shows the normalized co-occurrence scores of various categorical terms using pointwise mutual information, a measure from information theory that quantifies how strongly two terms occur together compared to their independent occurrences. So you can see in this table, autumn leaves score higher for brown, orange, and red, charcoal with gray, and so on. If there's no basic color associated with the term, then it's not colorable. We can augment the query with additional context, such as a category name or related words, using WordNet's ontology for additional disambiguation, which is a commonly used NLP technique, where WordNet is a lexical framework of English words that are interlinked based on semantic and lexical relations called synsets. The related term used to augment the query is a least common subsumer, or called LCS, between that data item and color synset. In other words, it is the most specific concept that is an ancestor of both the term and the color synsets. So here, fruit is the least common subsumer for the input term banana and the color synset. The final query input to Google Images consists of the term and the WordNet color synsets. And the Google Image Search API has provisioned for specifying the dominant color desired in the image search results as one of its parameters. We restrict the search results to clip art images since canonical colors are often easier to discern from clip art imagery. So here are the most relevant images returned from Google based on these input queries, and the canonical colors are extracted from the dominant colors in these images. Now for generating the color palette, we start with the highest scored canonical colors for each data item. We identify clusters with more than one color in them. So here, both apple and cherry have the same color values that are in the same cluster. We then check if there's an alternate color for the data item in that cluster. So apple, turns out it has another canonical color associated, which is green, because you have green apples. And so by assigning green to apple, you're spreading those color distances apart. We can then snap the data items to a predefined palette of colors available in a visualization tool like in Tableau by finding the closest corresponding palette color. And why is it useful to snapping to a palette? Rather than applying perceptual rules to tweak the values where, the value of grape here is rather dark, you can simply snap it to an existing palette, which is carefully designed to be perceptually good. However, effective visual communication is not just about color. It also involves layout and sizing, particularly when visualizations need to adapt to different screen sizes or formats. So semantic resizing aims to preserve key visual elements while ensuring that the visualization remains effective and legible across different display sizes. This concept of adaptive simplification has long been studied in cartography, where map generalization techniques determine which geographic features to preserve or modify based on scale. And not all elements of a chart carry equal importance. Some points, such as peaks and troughs and key labels, are more meaningful to the interpretation of data. So inspired by cartographic generalization, our algorithm assigns higher semantic weights to certain elements compared to less crucial elements like grid lines and minor tick marks. However, determining which elements to retain or modify also requires a quantitative assessment of how elements interact spatially. And this is where spatial metrics come into play. Density metrics help evaluate how cluttered a visualization is, ensuring that key information remains distinguishable. Collision detection identifies overlapping elements that may cause visual ambiguity, prompting adjustments to spacing or label placement. And area ratio calculations help assess how much space different elements occupy relative to the chart size, ensuring a balanced composition. So once we have a measure of these spatial properties, generalization techniques are then applied to adjust visual elements to maintain clarity while preserving semantic meaning. Jittering is used to slightly reposition overlapping elements. Elimination selectively removes less critical elements, such as these minor grid lines, to improve overall readability. So here is a demo of the algorithm in action, and as the video is playing, I will talk over it. Once the video loads with the internet, yep. So the slider is used as a proxy to reduce the size of the chart. And you find that as the size decreases, a lot of the less important elements tend to be minimized until the line chart becomes a tiny spark line where only the extrema are labeled. And then as the chart gets bigger, you notice that more detail is progressively added to the chart along with its minor grid lines and label marks. So we found that users in general found these charts readable and the methods effectively preserved important insights. And we're looking at adapting these to other types of charts, including incorporating user-driven preferences as well. So as I wrap up this portion of the talk, I wanted to kind of leave you all with some key takeaways regarding using semantics and perception for effective visual depiction of data. First of all, representation is context specific and really depends on the task and the underlying data. Like take the color example. Red for apple as a fruit would be very different when you're thinking about Apple as a company, where the logo might be more salient. It's always important to figure out what to emphasize as the most important information. And at any given point, we need to make sure that the level of detail is useful when less important information is de-emphasized, which tends to be the harder problem because you have to maintain context. So with that, I thought we can transition to the next theme of my research, which has been kind of the bulk of the work that my group has been doing lately, which is in the space of conversational interfaces, where we look at the problem of enabling more natural, interactive ways for users to explore and refine data using language-driven interaction. To make these interactions truly effective, systems must understand what the user is trying to accomplish. This is where analytical intent comes into play, where analytical intent is the analytical goal that a user focuses on when exploring their data. And intent can be expressed in many ways, where the user could explicitly choose attributes and values, or simply expressing their intent through language. But the problem is language can be vague, as its interpretation depends on the context and our inability to precisely determine the boundaries of such concepts. One of the most prevalent kinds of vague language are these adjectives. These concepts appear throughout language and are expressed on a spectrum of concreteness, from these superlatives like tallest and cheapest to graded adjectives like cheap, which depends on the context. You know, a cheap house in Bangalore is very different from a cheap house, say, in a smaller village in India. Safe means different things for different people. So that's often tends to be more subjective. In addition to language ambiguity, I've also been interested in ways to use context from the previous utterances based on a concept from natural language literature, which is called pragmatics. So pragmatics concerns the use of context to determine the intent of language. And this can be illustrated in this comic, where actually, yes, at the end of this comic, in the final frame, can only be understood in the context of what is happening in the previous frames. So how do we apply the notion of pragmatics for interacting with data? Say I'm looking at a map of earthquakes. This is around California, and I can start by asking large earthquakes near California. Notice that large and near are fuzzy concepts. And so the system makes a guesstimate and displays these sliders, one for large and one for near. And the earthquake magnitude is used to determine what near means, large means, so which is a magnitude of at least 5, and near is based on geospatial density in that area. And as a user, I can change the values of what that system interprets, and the system learns those preferences over time. I can also ask a follow-up where I say, how about near Texas? Notice that I didn't explicitly ask for large earthquakes, but the system remembered that by inferring intent from the previous context. And so one way of supporting analytical conversation is really taking the context of what is asked previously and using that context for subsequent utterances. And this is a similar way in which we interact with other humans as well. And I've been particularly interested in exploring how we can apply principles of pragmatics by modeling interaction behavior as a conversation. So for a sequence of utterances to be a conversation, it must exhibit coherence, where coherence is a semantic property of conversation based on the interpretation of each individual utterance relative to the interpretation of the other utterances. And we utilize and extend a model commonly used in discourse structure called conversational centering, which was initially presented by Gross et al., where forward-looking centers refer to the current focus of the conversation, and where each utterance other than the segment's initial utterance is assigned a set of backward-looking centers. Coherence is then inferred through the transitional states of continuing, retaining, and replacing between the forward and the backward-looking centers. And let me walk you through some examples to indicate how this works. So let's start with ellipses, where ellipses are incomplete utterances in the sense that either they miss some semantic information or they may be syntactically incomplete fragments. So often these utterances cannot be understood in isolation, but instead we need to consider previously established context. So here I'm looking at housing data in, around Seattle in Washington in the USA. So consider this utterance, houses less than 1 million in Ballard. And the system tokenizes that query where I get houses, 1 million, and Ballard. And then the user says townhomes. And here our model is performing two things. First, it applies a shift operation in the centering model to switch from houses to townhomes. And second, it retains the criteria of 1 million and Ballard to preserve the previous context and updating the dashboard. Another example is anaphoric referencing, where a user refers back to something in the previous utterance to avoid repetition. For example, for the query prices in 2015, the user types in previous year, and then we look at the phrasal chunk containing that reference to identify what entity that is referring to. And in this case, it finds the value of year in the backward-looking center, which is 2015, and then performs a shift, which is a calculation resulting in 2014, and updates the dashboard accordingly. So when we tested these conversational interfaces in open-ended tasks with actual Tableau customers and users, we observed that these user interactions happen to be multi-turn and context-dependent rather than isolated queries. So users often engaged in these long-threaded discourse segments with some query threads extending up to 18 turns. Importantly, about 35% of the utterances reference prior context, meaning that it was important to retain conversational memory to ensure coherent responses. In addition, giving good feedback to the user is also critical. At first, people were sometimes confused with the system behavior, but they quickly learned to watch the widgets. So here, a user types in United States following a previous query involving measles. The widgets confirm here that yes, it got the US and it remembered measles. So these research insights informed the development of Ask Data, which was Tableau's first production NLP feature. This was before LLMs. We now have like AI-enabled features, which were designed to enable users to query and explore their data through natural language. And since then, we've kind of looked into LLMs, looking at deep learning models that are pre-trained on vast amounts of data to support more intent understanding and semantics during these analytical conversations. In particular, I've been interested in exploring how NLP and generative AI techniques can be used to provide useful recommendations in a user's analytical workflow, surfacing new inquiries as seen in this research tool we built called Snowy that has since been productized at Tableau, where these recommendations that you see on the rightmost panel are generated based on what the user is currently doing in the interface. The system also generates these follow-up queries that you see on top. Notice that these recommendations are much terser. For example, rather than showing, show me worldwide gross over the years for each content rating in a movie data set, the recommendation just reads, compare across content ratings, supporting the principles of pragmatics that I talked about earlier. So beyond this work, a broader challenge in conversational interfaces is really understanding and supporting user intent, whether it's through language or an interactive dashboard. It's important that users have affordances to repair and refine system defaults, whether it's through clarifications or guided suggestions. And finally, for a truly cooperative analytical conversation, we must align language pragmatics, data context, and interaction. So we've explored how users interact with data through conversational interfaces, but another key challenge is how text and charts work together when communicating insights to a user. Text appears in many forms, including titles and labels to provide context, annotations to highlight key insights, narrative summaries to explain trends and patterns. But despite its ubiquity, text in dashboards is often an afterthought with limited tool support for authoring and integrating text effectively. With the rise of LLMs for text generation, understanding how much text to include, what type of content is most effective, and where to place that is more relevant than ever. So as we consider how text and visualizations interact in dashboards, it's important to examine how readers interpret and integrate text with chart elements. To build a foundational understanding, we started with these simple univariate line charts, which are both prevalent in the real world and provide a controlled setting for study. So let me illustrate with an example. This is a chart showing 30-year fixed mortgage rates with years on the x-axis. The chart has a visually prominent peak indicated by the arrow around 1981. The author may want to draw attention to this peak and write a caption. The 30-year fixed mortgage rate reached its peak of 18% in 1981. So this caption refers to the most visually prominent peak, and we expect people to focus on this peak based on the emphasis from both the chart and the caption and report takeaways related to the peak. But is this really the case? On the other hand, the author might want to point to this rise, in the late 1990s, indicated by this other arrow, a far less visually prominent feature, and write the caption, the 30-year fixed mortgage rate increased slightly from 1997 and 1999. Now the question is, would you rely more on the chart and would your takeaway be about the most visually prominent peak? Or would you rely more on the caption and would your takeaway be about the less visually prominent rise that the caption describes? To answer this question, 219 participants on Amazon Mechanical Turk were asked to mark up to 3 visually prominent regions in 43 line charts. 27 of them were synthetic line charts that we created and 16 were from the real world. And participants were provided a brief description of each marked feature. The responses were aggregated using a weighting approach where higher ranked features received more weight. A Gaussian smoothing function was applied to identify consensus regions of prominence. We then identified the top 3 visually prominent chart features and a non-prominent feature by crowdsourcing. So here the red, green, and blue boxes indicate the top 3 visually prominent features in order, and the gray dot shows a non-prominent feature. And then for each of these features, we use templates for caption generation in order to minimize the effects of linguistic variation. So here we fill in the domain, the feature, the start date, and the end date to obtain the caption. Macron's approval rating steeply dropped between June and August of 2017. Each chart was paired with different caption types, captions emphasizing the most, the second most, third most prominent features, as well as captions describing a non-prominent feature. Baseline captions were also included that simply stated the domain of the chart without emphasizing a particular feature, and we had a no caption condition as a control. Then we got a new set of over 2,000 participants where they were presented with a chart caption pair and asked to recall and type out their takeaway from memory on a brand new page. Responses were manually labeled to identify whether the takeaways aligned with the features emphasized in the chart or caption. So what we found was when the caption describes the most visually prominent chart feature, like in our initial example caption that describes the visually prominent peak, the takeaways tend to mention the feature doubly emphasized by the chart and its caption. So in our example, people tend to focus on the peak, which is both most visually prominent, and the feature described in the caption, including any additional external information. On the contrary, when the caption does not describe the most prominent feature, as in our second caption describing the small increase, readers tend to rely more on the chart and they report takeaways based on the visually prominent chart feature and almost completely ignore the caption, which we thought was interesting. So our findings on how readers interpret text and visual elements informed the development of Emphasis Checker, a tool designed to help authors align text and charts more effectively. And I'll just play this video and I'll talk over it again. So Emphasis Checker is almost like a grammar checker, like Grammarly. It identifies visually prominent features in charts and compares them with the key points emphasizing captions, highlighting mismatches that could lead to misinterpretation. So by providing this real-time feedback, the tool enables authors to refine captions to ensure coherence between the visual and the textual elements. And we have since deployed a version of this in Tableau, almost kind of as a lint checker so that the authors are aware when their caption is not aligned with the chart. So our exploration of text and chart integration reveals some key insights on how users prefer to consume text and visual information together. First, readers prefer text to be integrated with the chart, ensuring that annotations, summaries, and labels are directly linked to the visual elements. Text content subtly influences readers' takeaways, meaning that even a small difference in wording can shift how users interpret trends and causations. And we've done some follow-up work since then, where we have much more textured descriptors for various trends. For example, a sudden drop, is very different from just saying, the data just decreased. A crash has a very different semantic meaning from just a slight decrease and vice versa. So we've done some follow-up research where we have found that a notable minority of users also prefer to view text alone when describing data insights, suggesting that some readers may engage with text summaries before or instead of interpreting the visualization itself. So with these research themes in mind, I now turn to future research opportunities to explore how data exploration tools can support new semantic search paradigms, evaluate LLMs for visual analytics tasks, as well as exploring multi-agent workflows and novel data interfaces. So I've been interested in how semantic search tools can support a broader range of search intents. For instance, a user may ask specific analytical questions like tracking movie budget trends, explore a topic through existing visualizations like election results, or search by visual form, such as finding tree maps for stock data. As users engage with increasingly diverse sets of data sources ranging from text and audio for sensor and social media data, our information-seeking behavior has also evolved significantly. And so this evolution has required tools that can parse unstructured and semi-structured inputs, converting them into tabular forms and supporting more dynamic querying and interaction. So as we think about building more intelligent tools for search and analysis, it's important to recognize that valuable information exists across many formats, documents like PowerPoint slides or manuals, undocumented expert knowledge. All of this data is rich, but rather fragmented, which makes it really difficult to access and reason about. So I've been particularly interested in this problem of developing tools and algorithms that make it easier to search, analyze, and interpret complex data. All this leads into where I see some exciting future research directions. First, we need novel ways of enriching semantics across entire information-seeking workflows, not just during querying, but also as users explore and interact with information. Second, our systems must be able to recognize and integrate dynamic semantic concepts like shifting domain vocabularies. And finally, I'm particularly interested in how we can support more personalized and adaptive search behaviors that learn from users over time that incorporate collaborative filtering or preference aggregation. For example, someone initially unfamiliar with their data may need a different set of recommendations compared to when they become more familiar with the data and the types of questions they want to ask. Building on this idea of personalized and adaptive workflows, I want to highlight how LLMs are now capable of performing many analytical tasks, where users can upload a data set, use natural language to clean and prepare data tables, and even generate code and visualizations. So as we think about using language models in visual analytics, a key challenge is evaluating how well they actually support analytical workflows. So I'm particularly interested in understanding what data practitioners and developers look for in these models and how these expectations shift for different types of tasks. So one of the recent projects that we've been working on in our group is exploring how to create more nuanced evaluation metrics for analytical tasks. So instead of just checking if the answer is correct, can we evaluate how well a model handles ambiguity, preserves semantics, selects appropriate visualization types for specific questions, and summarizing the data effectively? Looking at ways to employ both humans in the loop as well as models cross-validating each other's inputs are important topics to further understand. So as we think about advancing data analysis, one other exciting direction is supporting multi-agent exploratory workflows. This involves not just a user interacting with the system, but multiple agents, human and AI, contributing to the sense-making process. But of course, it's equally important to design safeguards around hallucinations and inaccuracies, especially when these models become decision partners. So instead of a single model handling user queries, multiple agents could collaborate, where one could refine insights, another could structure responses, while yet another can ensure contextual alignment, for example. So this multi-agent paradigm has shown some initial promise in enhancing robustness and accuracy in these data-driven narratives. So here's some initial work showing multi-agents in action. A user asks a question in the context of a Jupyter notebook or initiates an analysis in this interface. Different LLM-powered agents take on specialized roles, where an insight agent extracts statistical findings and key patterns, a narrative agent generates human-readable summaries, while a verification agent cross-checks outputs for inconsistencies. Users can review, edit, and refine this AI-generated content, providing feedback and adjusting the parameters in real time. And we've since open sourced this tool. If you're interested, I'm happy to share that GitHub link. This was recently presented at CHI. So these directions point towards a broader research agenda around the future of data work. How do we balance autonomous analysis with the nuance of human judgment? There's an opportunity to explore how agent-driven workflows can refine their understanding of user intent, learning iteratively through interaction and feedback. And finally, we need tools that don't just generate insights, but distill effective takeaways for decision-making, tailoring outputs to the needs of specific audiences. So as data experiences continue to evolve, new opportunities are emerging across the spectrum of automation, augmentation, and human agency. We're already seeing embedded analytics seamlessly integrating in workflows such as push notifications in Slack or Microsoft Teams. But beyond traditional 2D screens, spatial computing devices like the Apple Vision Pro are redefining how we engage with immersive data storytelling, challenging long-standing assumptions around visualizations and interaction paradigms. At the same time, the increasing prevalence of sensors enables novel real-time interactions. And so these evolving paradigms present exciting research opportunities to expand the boundaries of intelligent, adaptive, and human-aware data interfaces. So before concluding, I wanted to take a moment to thank all my wonderful collaborators who have contributed to this research. The work I've presented today has been shaped by some incredible partnerships with colleagues across Tableau, academia, and the broader visualization, NLP, and HCI communities. And also, before I close, I really want to take a moment to acknowledge and thank Professor S.V. Rangaswamy, as indicated, former faculty member here at IISc, but far more than that, he has been my mentor, my unwavering champion, and my father-in-law. And his guidance and encouragement and belief in my work has really shaped my research journey. So thank you for listening. Happy to take any questions at this time.
Creating